Another Day, Another Story. A Brief History of Time, Part 4. Certainly. Here are the topics covered in Chapter 3, The Expanding Universe, by Stephen Hawking, presented with subsection numbering. 3.1. The Calculation of Stellar Distances, from Herschel to Hubble. 3.2. The Redshift of Galaxies and the Expanding Universe. 3.3. The Static Universe versus Friedmann's Non-Static Model. 3.4. Microwave background radiation and the confirmation of Friedmann's assumptions. 3.5. The three models of universe evolution: expansion, collapse, or static. 3.6. Curvature of space and the Big Bang singularity. 3.7. The steady-state theory, competing with the Big Bang. 3.8. The failure of alternative theories to the Big Bang. 3.9. Black holes and the origin of the universe, Hawking and Penrose's contributions. 3.10. Quantum effects and the disproof of the singularity. Please note that the content within each section may vary in length and depth, but these headings should give you an overview of the topics covered in Chapter 3 of the book. Chapter 3. The Expanding Universe. 3.1. The Calculation of Stellar Distances, from Herschel to Hubble. In this chapter, Hawking first describes how physicists and astronomers calculated the relative distance of stars from the Earth. In the 18th century, Sir William Herschel confirmed the positions and distances of many stars in the night sky. In 1924, Edwin Hubble discovered a method to measure the distance using the brightness of Cepheid variable stars as viewed from Earth. The luminosity, brightness, and distance of these stars are related by a simple mathematical formula. Using all these, he calculated distances of 9 different galaxies. We live in a fairly typical spiral galaxy, containing vast numbers of stars. 3.2. The redshift of galaxies and the expanding universe. The stars are very far away from us, so we can only observe their one characteristic feature, their light. When this light is passed through a prism, it gives rise to a spectrum. Every star has its own spectrum, and since each element has its own unique spectra, we can measure a star's light spectra to know its chemical composition. We use thermal spectra of the stars to know their temperature. In 1920, when scientists were examining spectra of different galaxies, they found that some of the characteristic lines of the star spectrum were shifted towards the red end of the spectrum. The implications of this phenomenon were given by the Doppler effect, and it was clear that many galaxies were moving away from us. 3.3. The Static Universe versus Friedmann's Non-Static Model. It was assumed that, since some galaxies are redshifted, some galaxies would also be blue-shifted. However, redshifted galaxies far outnumbered blue-shifted galaxies. Hubble found that the amount of redshift is directly proportional to relative distance. From this, he determined that the universe is expanding and had a beginning. Despite this, the concept of a static universe persisted into the 20th century. Einstein was so sure of a static universe that he developed the cosmological constant, and introduced anti-gravity forces to allow a universe of infinite age to exist. Moreover, many astronomers also tried to avoid the implications of general relativity and stuck with their static universe. One notable exception was the Russian physicist Alexander Friedmann. Friedmann made two very simple assumptions. The universe is identical wherever we are, i.e., homogeneity, and that it is identical in every direction that we look in, i.e., isotropy. His results showed that the universe is non-static. His assumptions were later proved when two physicists at Bell Labs, Arno Penzias and Robert Wilson, found unexpected microwave radiation not only from one particular part of the sky but from everywhere and by nearly the same amount. Thus Friedman's first assumption was proved to be true. 3.4 Microwave background radiation and the confirmation of Friedman's assumptions. At around the same time, Robert H. Dicke and Jim Peebles were also working on microwave radiation. They argued that they should be able to see the glow of the early universe as background microwave radiation. Wilson and Penzias had already done this, so they were awarded the Nobel Prize in 1978. In addition, our place in the universe is not exceptional, so we should see the universe as approximately the same from any other part of space, which supports Friedman's second assumption. His work remained largely unknown until similar models were made by Howard Robertson and Arthur Walker. 3.5 The three models of universe evolution: expansion, collapse, or static. Friedman's model gave rise to three different types of models for the evolution of the universe. First, the universe would expand for a given amount of time, and if the expansion rate is less than the density of the universe, leading to gravitational attraction, it would ultimately lead to the collapse of the universe at a later stage. Secondly, the universe would expand, and at some time, if the expansion rate and the density of the universe became equal, it would expand slowly and stop, leading to a somewhat static universe. Thirdly, the universe would continue to expand forever if the density of the universe is less than the critical amount required to balance the expansion rate of the universe. Asterisk 3.6 Curvature of space and the Big Bang singularity. The first model depicts the space of the universe to be curved inwards. In the second model, the space would lead to a flat structure, and the third model results in negative, saddle-shaped curvature. The first model included the beginning of the universe as a Big Bang from a space of infinite density and zero volume known as singularity, a point where the general theory of relativity, Friedman's solutions are based on it, also breaks down. Asterisk 3.7 The steady-state theory, competing with the Big Bang. This concept of the beginning of time, proposed by the Belgian Catholic priest Georges Lemaitre, seemed originally to be motivated by religious beliefs because of its support for the biblical claim of the universe having a beginning in time instead of being eternal. So a new theory was introduced, the steady-state theory, by Hermann Bondi, Thomas Gold, and Fred Hoyle, to compete with the Big Bang theory. Its predictions also matched the current universe structure. But the fact that radio wave sources near us are far fewer than from the distant universe, and there were numerous more radio sources than at present, resulted in the failure of this theory and universal acceptance of the Big Bang theory. Asterisk 3.8 The failure of alternative theories to the Big Bang. Yevgeny Lifshitz and Isaac Markovich Kalatnikov also tried to find an alternative to the Big Bang theory but also failed. Asterisk 3.9 Black holes and the origin of the universe, Hawking and Penrose's contributions. Roger Penrose used light cones and general relativity to prove that a collapsing star could result in a region of zero size and infinite density and curvature called a black hole. Hawking and Penrose proved together that the universe should have arisen from a singularity, which Hawking himself disproved once quantum effects are taken into account. Asterisk 3.10. Quantum effects and the disproof of the singularity. Hawking's work on quantum effects in the context of black holes led him to propose that the singularity predicted by general relativity is not a true physical state but rather a breakdown of classical physics. According to quantum mechanics, particles and fields undergo fluctuations, and this applies to the fabric of spacetime itself. These quantum fluctuations near the singularity would cause the curvature of spacetime to become extremely large and chaotic, rendering the concept of a singularity invalid. Hawking's insights into quantum effects challenged the notion of a definite beginning point for the universe and opened up new avenues for understanding the early moments of cosmic evolution. Thanks for watching.